Today I'll be finding the integral of a function like this, an exponential function. So y equal ax. And without further ado, let's begin. So we split this up into multiple rectangles, and I'm gonna make each the base of all these rectangles h. We'll have a constant base. Each of these rectangles will have the same base, even though my diagram is drawn horribly. So this would also be h. That would also be h. All right. So the integral of 0 to x, and let's make the stopping value here. Let's say x. X is where we want to stop. And of ax dx would obviously be the sum of these rectangles, h times ah, because base, which is h, times height, which is ah, because height is y, right? Height is y. So at x equal h, the height would be ah. And likewise, at x equal 2h here, the height would be a2h. And so forth. To our stopping value h, a, x. Okay. Now, let's just denote this as s. S meaning sum. And because I don't want to write all of this out, it gets kind of tedious. So let's say sum equals this, and yeah, let's make that sum. And sum equal h plus ha2h and ha3h is the next term. Hopefully you notice the pattern. And let's multiply SAH to both sides. So we get this equals ha2h plus ha3h. And you should know that we can notice here that we can telescope some things. So what would SAH minus S be equal to? Well, HA2H cancels out with that. HA3H cancels out with someone in here. 4H cancels out with someone in here too. And AX cancels someone with here. So the only terms we're left with is this. HAX, AX plus H minus HAH. Alright? And remember, we're trying to find an integral, which we denoted as S. So let's factor out S, H minus 1. And this should look, what I'm doing here should look familiar to you. This is the geometric series, or something similar to the geometric series. Then we get S equal AH minus 1. Let's factor out the H, and we get this. All right? Okay, now I want to further factor out this AH here. We get this, H, AH. And then we can use L'Hopital's rule. Because if you notice here, as h approaches 0, this becomes a to the power of 0, and a to the power of 0 is 1, 1 minus 1 is 0. As AH approaches 0, this becomes 1, but as h approaches 0, the numerator becomes 0 too. So we can use the L'Hopital's rule. So let's take a derivative of the top here and a derivative of the bottom. So obviously, derivative of the bottom would just be AH, where, hold on, let me think. Okay, let's just assume that the derivative is ln. Hopefully, you should know what the derivative is. So it's ln a times AH, and just negative 1 just gets out because it's a derivative. The derivative of constants are 0, or is 0. And on the top here, we have to apply chain rule. We're taking derivative with respect to h. So chain rule, so we get h just becomes 1, so ax minus 1, plus, now we take a derivative of a of h, and that would just be h times ln a times ah over, times ax minus 1. All right, now, luckily for us, and this equals the sum. Luckily for us, this AH cancels out here. So we get equals AX minus 1 over ln A. Okay? And ln A and AH cancels out here. So we get plus H. Oh, wow. That's pretty simple. And lim as H approaches the 0. Well, this term just becomes 0. So, and then we just get AX minus 1 over ln A equals S equals integral of 0 of x ax dx. Now, if you're hesitant to use L'Hopital's rule because it includes a derivative, then there's another method to find the area under the curve, and that's using substitution. So but first let me explain what this means. You might be confused why there's a -1 here. You might agree with this ln part because it's just a reverse derivative. So yeah, but this -1 means that, let's say ax, or let's say x equals 0. So if x equals 0, a0 would be 1, so 1 minus 1 would be 0. And that makes sense because at 0, there's no area under the curve. The area equals 0. So this should make sense to you, that there's a -1 here, instead of there being no -1 at all. It's because we chose the lower limit to be 0. Okay? So now onto another method to get from here to here. Because you might think it's circular reasoning to use L'Hopital's rule, and it isn't. But okay, let's just ignore that for now, and let's compute the get from here to here through another method, and that other method is setting z equal to ah minus 1. And now I want you to notice here that as h approaches 0, lim z approaches 0. So because look, as h becomes 0, a to the 0 is 1, minus 1 is 0, and then z equals 0. So lim as h approaches 0, z approaches the 0. Alright, so let's substitute. So we can put z on the bottom here. Oh, and before we do any substituting, let's convert z plus 1 log a equal h. So move the 1 to the left side, take the log on both sides, and I get this. Alright. So this becomes here to here, and let's replace all the h's with what we have here. So z equal ah minus 1, z, h equals this, so log a z plus 1 times a to the h. Well, look here, if h equals this, then a to the log of a just equals 1. So this just ends up being z plus 1, right? A to the power of log of a is just, they cancel out, so 1. And then finally, we have this, which just remains untouched, okay? And let me rip this out. We need more space. Okay, now let's factor out z plus 1. So we're gonna have z log, and lim as z approaches 0, log a z plus 1. I brought the z in front, times ax minus 1 over z. And then plus 1, look, I factored z in 1. So I get log a. Okay, I'm just going to be consistent here and don't write parentheses. Ax minus 1 over z. All right. Now, this left term just becomes log a z plus 1, ax minus 1. And I want you to notice here that as z approaches 0, this becomes log a1. But log a1 equals 0. Because log to the power of... how do I explain this? Okay, log a... Whenever 1 is here, then there must be a 0. And you can derive this using exponent rule. Because a to the 0 is 1, so a to the 0 is 1, so log a1 is 0. So this term just becomes 0. Now we only need to consider this term. So how do we do this? So by what do you call it? That one of the log properties, we can do 1 over z times ax minus 1, and then we can bring 1 to the z as the exponent. So log, sorry, there should be a z plus 1 here. Log a z plus 1, and the exponent 1 over z, lim z approaches 0, ax minus 1. And something you notice here is this is just e, because e equals lim h approaches 0, 1 plus h over 1 over h. And this is just different variables. So this just becomes log a e ax minus 1. But what does log AE equals? So let's set log AE to equal some f, all right? Then obviously a to the f equals, wait, am I doing this right? Yeah, I think I am. Equal e, then we take ln on both sides, 1 f ln a, and then f also equals 1 over ln a. And then, so if f equals log AE, then that means log AE equal 1 over ln a. So this just equals ln a, ax minus 1. And that's same exact thing as what we got here. So this is the integral from 0 to x of ax dx. And if you want me to explain why there's a negative 1 here, it's because at x equals 0, a to the 0 becomes 1, 1 minus 1 is 0. And that makes sense because there's 0 area when we're going from 0 to 0. Thank you. So here's the proof. So this is looking like the proof for geometric series. And yeah, thank you.